Ah, you gotta be kidding. I'm gonna draw my picture over again.
No, the window's not cracked. That's how I made sure. Actually.
Don't worry, I'm gonna draw the same picture.
Next 50 minutes trying to work the window back up.
Yeah, there it goes. I'm gonna make mine a little bit bigger, actually.
Yep. Yep.
Alright, here we have a car parked in San Francisco on one of those hills. It weighs 2,000 pounds, and we want to know if the brakes are going to hold. So we need to know how much force is on the brakes of this car trying to pull it, well, downhill. So, when you draw this vector, because that's really the only vector that we have, how would we draw it?
You would draw it. You draw it at the car.
And where does it go? Remember, vectors always have direction.
Towards. It would go towards your vertex of your.
Oh, you mean you think the 2,000 pounds would come straight down the hill?
No, it would go.
It would go straight down.
Yeah,
because of gravity. So if this point represents the car, this vector would represent the 2,000 pounds of force. All right. So we have literally a direction and a magnitude for that vector, specifically straight down. We want.
Those are two. There are two vectors in this situation.
Yeah. Well, there's going to be. Yeah, two vectors. Where's the other one going to go?
It'll go along the angle of your hill towards the vertex.
So the other force is going this direction. Now, how it goes in that direction is determined by two things. The weight of the car is trying to go straight down, but it also applies weight to the ramp. And the weight to the ramp actually goes in this direction. And what happens is those two last vectors I've drawn, this one and this one,
90 degrees.
have to add up to it at 90 degrees. They have to add up to the green vector. So we get a little rectangle going on there. And this is always what happens. Now, the trick is this. If this angle here is 20 degrees, we have to figure out in our picture up here, where's the 20 degrees? Is it here or is it here?
First one.
Then it becomes fun. We get to go back to geometry. Let's prove it. If, think about this for a second. If we take a triangle and design it in this way, where this is a right angle and this is an altitude, what happens is it creates a ton of similar triangles in there. So if this angle is 20 degrees, and this is a right angle, and that's a right angle up there, and this is 20 degrees, this angle over here has to be 20 degrees. Well, did I do that right? No, wrong one.
It's the one up.
It's up here.
Yeah.
20 degrees. Because the right angle is down here.
And that same angle.
And this angle here
that would be
is
the same as that one, yeah.
that one up there. So whatever this is, x degrees, x degrees.
70.
But what I'm interested in is, if we drew this one, that's a right angle. No, it's not. Hold on, I'm screwing myself up.
It would be a right angle.
Back up, back up, back up. That's a right angle, I don't care about that one.
So yeah.
This is the one I was interested in. So since these are both x degrees, then the 20 degrees has to be here.
So I was right.
Yeah, you were right. And usually when you draw the picture, you can tell which one's the bigger and smaller one. It's just if you do your picture really bad. Alright, so what I need is, how long is this side according to this 20 degrees? So we have this triangle that looks like this. And the right angle is here. And 20 degrees is here, and we know that this side is 2,000 pounds of force. What side am I interested in?
The ramp side?
The ramp side, which would be this side here. So I'm curious how much force is being pulled down that side. So how would I solve?
Put x there.
Put x here.
And solve it using sine.
Sine. So this becomes sine of 20 degrees is equal to opposite, which happens to be x, over hypotenuse, which happens to be 2 grand. So x equals 2,000 sine of 20, and x is approximately how many pounds?
684.
684 pounds. So if your brakes cannot withstand 684 pounds or more, or I'm sorry, if your brakes only withstand less than that, then your car is going to go downhill. Another way of thinking about this is if your car's brakes are gone and you attach a rope to it, the rope would have to hold 684 pounds of force.
That'd be a strong rope.
So a thin rope, thick rope.
Depending on,
How strong the rope is.
well, you can have brakes as strong as whatever. They can hold 2,000 pounds.
Oh yeah.
But as soon as you get to a certain angle, you have to worry about the traction of the tires.
Friction. We're not going to do friction coefficient here. That's
Okay.
the end of the buck. Good thought. Good thought.
Yeah. Yeah, through the roads.
Really amazing.
You could wear
Ah.
your all your clothes by yourself.
That's a possibility. Here's the last one. I don't think it's in the book. It might be. Do you guys just talk when I'm trying to think?
Mhm.
Yeah. Which distracts the heck out of me. Because I can't think.
Sorry.
Static system. I really don't think this is in the book. Even though they kind of hint at it, they don't really have an example of it.
What was it to before?
Nope, I don't see it. But I'm going to make you do it anyways. So if I have a building, and he wants to advertise his store, so to this building he attaches a sign, and to attach it he's going to have these 2 poles attached to his building, and his sign is going to be here. I'm making the sign huge. But it's got to hold that sign out at arm's length away from the building. Alright, so the sign weighs, let's make it 400 pounds
Okay.
of force. Let's let this angle here be,
30 degrees.
now that'd be too boring, 35 degrees.
21.
To make it 30 degrees, we can use a special triangle, and that's no fun.
It's like, how about 32.6 degrees?
Yeah. No, I'm not gonna get that weird. Alright, so just like any of these others, we're going to set up a system of vectors, and the system of vectors is very unique. This 400-pound sign is not moving, kind of like if we have brakes of 684 pounds on this car and it's holding it, that car is not going to move at all. So this is what's called a static system. I want that sign to stay right here, and my interest is how many pounds of force is being applied to my support struts.
Ooh,
Alright,
interesting though.
so you have to think about what's going on. The sign is going to be trying to pull itself down, so that vector is going straight down. If it's going straight down, what kind of force and which
Tension.
direction would the top beam have?
Tension going that way.
The tension would go this way, but you want it to pull opposite, because if you push the direction that you're going, the sign's going
The
to
tension
fall.
from the sign is giving that vector. And so
Opposite is what you want to go with. So the sign vector and the weight vector, the weight vector is going straight down. The sign vector is going to be going straight into the building because it's trying to pull it into the building. And then the last one is this diagonal one. And if you think about it, the sign's trying to push down on it, and physics means it has to go back up, opposite and equal reaction, all that fun stuff. So more than likely it's going to go in this direction. Now, the post holding it to the building and the weight of the sign going down, those don't have any angles. So how do I deal with the last one? Well, remember, we want this angle.
That angle is going to be.
You have the 90-degree angle
55
from the building.
degrees.
Yeah, it's 90 degrees. This angle over here is
35.
35 degrees. It's the angle between the vector and the building.
So the other one is 55, like I said.
55. I didn't hear what you said number-wise. Sorry. Okay, so I need an equation for each one of those vectors. Let's do the easy ones. This is, let's call this one V. Let's call this one W for weight. Let's call this one U for weird. I don't know. So the V and W are simple. V vector is equal to what? Oh, actually, no. That one's actually the hard one. Hold on. Let me back up.
Whoa.
Yeah, that one's the hard one.
Oh my gosh.
We'll come back to it in a second. The W vector is easy.
W's going straight down at 400.
So what would be the components? 400 pounds of force straight down.
So 0, 400?
0, 4. Kind of. 0, 400 would be going straight up.
0, -400.
0, negative 400 would be going straight down.
I had 400 right though. So yeah.
This is the only one we know the magnitude of. This one is guaranteed to have a magnitude of 400. The other two, V up there and U down here, we don't know their magnitudes. So what should I call the magnitude of V? Well, I highly suggest you use magnitude of V. And this one's going to have a magnitude of U. What should I put next to them?
Oh, you put next to them the parentheses, cosine.
Which one's going to need the cosine sign?
The V?
V, you could if you
Oh,
wanted to, but
well,
you really
U.
don't need to.
U.
U's definitely going to need it. So this one's going to be cosine of
55.
55
Oh,
and sine of 55. What about V up top there?
B cosine of 35 sine of 35.
No, because V is pointing directly to the
Oh, yeah,
west.
that's right.
V's pointing. So you could, if you wanted to, I guess, cosine of
90 would be
what angle's going that way?
180.
180. I mean, you could do cosine of 180, sine of 180, but cosine of 180 is -1, and sine of 180 is
0.
0. So if you really want to,
It's -1 and 0.
-1, 0.
And
And
you
the
said that was
magnitude
hard-
will make sure it's long enough in that direction.
You said that was the hard one though?
Well, I forgot the magnitude of V. I was looking at the easy one. Components, easy as the weight going straight down. All right, so here's the trick. The sum of these vectors has to equal what for this thing to sit still?
400.
Now, remember with the tugboats, when we're pulling something,
that's not
And-
more than 400.
we have all this force going into it, and it actually started moving in a specific direction with a specific force. I don't want that sign moving.
Okay.
So if I add all these vectors together, what do I want their resulting answer to be?
Over 400, right?
Ah, simpler.
Less
I
than-
don't want it moving. If I give it a value, it's moving.
So you want it to be
0.
What kind of 0?
There's
0 is a
different zeros?
scalar number. If you add vectors together, you get a vector. It's called a 0 vector, which has components of
0?
and 0. So it has 2 zeros as its component. So one thing to be careful with, this is a scalar. This is a vector, and it's specifically 0, 0. So 0 vector is a little bit different than 0 scalar. 0 scalar, 0 times anything is 0. 0 times a vector makes the 0 vector, 0, 0. But one has magnitude and direction, even though the vector has no magnitude and no direction. It's still considered a vector. It literally just becomes the origin. So I want that object to go absolutely nowhere, so the sum of these vectors has to be the 0 vector. So when I add these all together, The resultant answer should be the 0 vector. Put a little plus sign here too. All right, so let's add them together. So v plus w plus u, I want it equal to the 0 vector. V is the magnitude of v with components negative 1, 0, or yeah, negative 1, 0. V is just 0, negative 400.
Mean W?
W, I'm sorry. And u is the magnitude of u, cosine of 55, sine of 55. And we might want to change that into decimals eventually. And we want that answer to be equal to that. I just ran out of order.
Okay.
I just want to make sure it even fit on my little thing over there. Okay, so let's start combining things. Now, literally what happens is you combine the first component of each one of these vectors, and then you go through and combine the second component of each one of these vectors to come up with the new first component, second component. So the first component off of the first one is going to be negative magnitude of v. From the second one we get 0. From the third one we get,
Magnitude u.
what's cosine of 55 with 3 decimals?
Oh, it's 57.
Huh?
0.57.
0.57?
4, I'm sorry.
So this would be
0.57.
plus
0.57.
0.574.
Yeah.
Magnitude of u. And then that's it, right? That's the first 3 of it. Comma. Second components. What do I got?
Why is it a negative magnitude of V again?
Which one? Here?
Yeah, the very first one.
When you do magnitude of v times the first component, you get negative 1 times the magnitude of v, which is negative magnitude of v. The second component was, first component of the second vector was 0. The first component of the third vector was cosine of 55, magnitude of u. All right, now we're on to the second part of the vector. So we're going to get magnitude of v times 0. 0. That's nice. I'll just put it in here to remind myself I did it. Second component of the second vector.
Minus 400.
You get minus 400. And the second component of the third vector. Well, what's sine of 55?
Oh, 0.819.
So this will be plus 0.819 magnitude of u. And this is going to equal the 0 vector. 0, comma 0. Now again to something simple. If I give you 2x minus 3y is equal to ax plus by, what can you tell me what a is equal to?
Something.
And what specifically something? If I have this equation, and I tell you that it's
A is equal to 2.
A is equal to 2,
And B is equal to negative 3.
and b is equal to negative 3. Because the coefficients of the polynomial have to be equivalent if they're equal. Well, the same thing happens here. The first component on this side is this ugly mess. The first component of the 0 vector is
0.
so they have to be,
The same.
they're equal. So you get negative magnitude of v plus 0.574 magnitude of u has to equal
Is it 7.74?
0.
Oh, it's 74. I put 1 for some reason.
You're the one that told me. So we get the first component of the left vector is equal to the first component of the 0 vector. We also get negative 400 plus 0.819 magnitude of u, the second component, is also equal to the second component of the 0 vector.
Oh, you solve for magnitude of u, and then you plug in the magnitude of u as the other side, solve for the magnitude of v.
Ta-da. So if I solve for the magnitude of u, the first thing I'm going to do is add 400 across, and then turn around and divide by 0.819. So what's the magnitude of u equal to? It's going to be 400 divided by 0.819. Approximately.
488.4.
488.4. So this, I can now use that equation to a different color. So here I'll get the magnitude of v Ooh, V. Alright, screw that up. Plus 0.574 of U, but U was 488.4. This green marker squeaks too. I switched it earlier. And this is equal to 0. How do I solve for the magnitude of V? Think of it as a big ugly variable.
Yeah, you bring.
Bring this over to the other side. That would make it really easy. So the answer is just going to be the product of these two. So the magnitude of V is going to be,
Well, you have to, don't forget the negative too.
I'm shifting the magnitude of V to the other side. Makes it positive.
Although you're shifting that part over there. but
Yeah,
you just
I'm
put it
shifting
on the
him
side.
over to the other side. And then all I have to do is multiply these two together.
That's 280.3.
280.3. Each of these is pounds. So U represents the diagonal post. The diagonal post has to hold 488.4 pounds or more to be safe. Usually engineers go more. And the horizontal one has to hold a minimum of 280 pounds
Of tension.
of tension, I guess. Of force. I like saying force. All right. Not too bad, right? The only problem with that is it's a lot of writing. But once the pieces start coming together, it starts to make a little bit more sense. So, how can I make it harder? One of my favorite test questions.
Illinois Jones.
I can't use Indiana Jones because, well, it's trademarked.
Just say copyright.
Gorge. On a rope. Soap on a rope.
Oops. Spelled that wrong already.
I thought that's it right first. This is for
Below.
Updraw picture. It'll make more sense.
Oh, okay. So below sea level?
How much force is each side of the rope experiencing?
So assuming that he's like ranger crawling across this rope.
Yep, ranger crawling. So here's the gorge. Draw it kind of big. And maybe there's crocodiles down here or something.
Yay!
We gotta have Indiana Jones here.
Oh, no, it's Illinois Jones.
And you have a rope connecting the two sides, so one part of the rope is here, the other part is over here. Now once he starts crawling across this, the rope is going to go down because he's going to weigh, and it's going to stretch a little bit, and it's going to pull down a little bit. Hopefully it'll hold him. And that's the whole point. We want to find out if this sucker's going to hold him. So he is
300 feet.
300 feet across 1,000, and he's going to come down a certain distance, so let's put him here. It's an exaggerated picture. But it's better to be exaggerated than trying to be accurate with it. And he's here. I could draw a little picture of him holding on.
Yeah.
Little stick figure.
Yeah.
Give us a little.
But he'll get in the way.
Stick alligators.
I'll draw stick.
He's holding on by his head.
Yeah, I was about to say. Hold on by his teeth.
He's really good. Alright, so what I mean by, where is it? He is 300 feet across and 45 feet below. That means this distance here is 45 feet.
Below the edge of the
Below the edge of the curve. The
gorge
gorge.
cliff thing.
There you go.
That is a That is an alligator shark thing.
Alright, so this distance here, from here to here is 300
C.
feet. This distance from here to here is
700.
700 for a grand total, of course, of the 1,000 feet gap.
Yep.
Okay. What do I need to find?
The angles.
The angles. And that's where the fun of this problem becomes.
And,
So let me erase all of this.
Well, you have your two triangles.
Yep, you have two triangles. You have a couple sides.
Yep.
You should be able to find the angles. Now the angles we're interested in, if we put this in the coordinate system, here's Indiana Jones.
Illinois Jones.
Illinois Jones. Keep correcting me because I'm going to keep saying Indiana. His weight is trying to go this direction. There's two ropes, and they kind of come out exactly like that, except they go opposite directions. So the rope over there is going up. The rope over here is a little bit more slopey. So the angles of interest are here and here.
Which would be the same angle as up.
If you want, you could just put it here and here.
And then it'll be
It
the
makes
same-
life a little bit easier.
It'd be the same angle as from the level
Yeah.
unstretched rope to, yeah.
So you're trying to find
Oh.
that angle.
Little review. This angle is called the angle of
Correspondence?
down, look up, look down. Remember I talked about these. Angle of,
Elevation.
you're looking down.
Uh,
You're at the cliff face and you're looking down. at
Depression.
Depression.
yeah.
And the angle of depression is the same thing as the angle of. Elevation.
You have to set it.
So depending on what you want to do, you can find the angles at the top. I like doing the horizontal line and finding these two angles. It really doesn't matter.
Well, why not just find the top ones if you're at the picture's drawn right there?
Yeah, or you
I
have
like-
triangles like that.
I like trying to get the picture to look like that. Just go with me. It doesn't matter. So, if I look at this side of the triangle, how long is it?
45 feet.
This is 45. The bottom is
300.
300. How do I find the measure of this angle?
You do tangent.
Tan. So you would say theta is equal to tan inverse of what?
Of 45 over 300.
45 over 300.
I don't know why I tried to country with
Approximately?
It is 8.5.
8.5 degrees. So in this picture, this would be 8.5 degrees.
That is an overly exaggerated angle to be 8.5 degrees.
Well, I told you I wanted to do that so you can start seeing, all the
What's
pieces.
that?
If you make the picture too small, it's really hard to see what's
He's not
going
even
on.
dropping down that much then.
No, he's not.
Yeah, I was gonna say that's a
Very
slack
little.
rope.
My pictures, it's a slack rope. What's really happening is not.
What's
All right, how do I find
It's just going down by like
the other angle? This side again is 45, but the bottom piece now is 700. So the other angle, I'll just call it beta. Why not?
Ooh, how about
Tan
the
inverse
prime?
of
Shut up. It'd be
Jeez.
opposite,
It is 45 over 700.
700, yeah.
45 over 700. Approximately
3.7.
3.7.
Yes.
My picture's really exaggerated.
Yep.
Which means it's a really decent rope.
He's just going down by like this much.
Well, he's going down 45 feet, but the angle from 1,000 feet across is going to be very small.
Here's the real question. How high up is the rope at level from the
Yeah. Does he go down? Yeah.
Does he touch the
We hope not.
I say if it's only like 50 feet, then the gators are probably jumping at him.
It'd be interesting to find out, wouldn't it? No, thank you. All right. So now we need to come up with names for our vectors. It doesn't matter which one you call what, but I like calling the weight W. Which one's the easy vector here?
The W?
So what's W equal to?
I don't know.
45 feet straight down.
No, it has nothing to do with feet.
How much does he weigh?
Exactly.
He weighs 200 pounds.
Oh, okay.
It says in the problem.
I
So what's the vector?
200.
0 to 100. 2 to 0.
0 to 100 real quick.
Which way does 0 to 100 point?
It's
Zero
negative.
negative
It's
0
negative.
to 100 points that way. It's 0, negative 200. Also known as negative 200J.
Yes.
Oh, negative 200, negative 200.
J with a hat.
J with a hat.
Fancy J.
All right, what about U?
Oh, I went like 140.
Don't care about vector
I'm
U.
done. I'm done.
What do we know about vector U?
We know it's angle,
We know it's angle,
Oh my
which is
8.5.
Yeah.
So what do we do with an angle to come up with a vector?
the cosine and the sine.
The cosine and sine piece.
So it's going to be the magnitude of U.
Magnitude of U,
Oh my gosh, we're doing the same thing.
basically.
Vector cosine of 8.5, sine of 8.5.
Close, no cigar.
What?
What quadrant are we in?
Cigar?
Oh, negative 8.5.
No, what quadrant are we in?
We're in the second.
We're in the second quadrant. So 8.5 degrees in the second quadrant.
Negative.
No.
Sine.
Oh,
171.5. Yeah.
So this becomes 171.5. You gotta be very careful
Smarticles.
about where you are. Smartles. Alright, what about, what's the last one? V.
That's magnitude of V. Cosine of 3.7.
And is it really 3.7?
It is
Yes.
really 3.7.
Alright, 3.7 degrees,
And then
because
sine of 3.7.
it's in the first quadrant.
Yeah.
If it's out of the first quadrant, you gotta be careful. Alright, little suggestion, just to make your lives easier. I'd highly suggest you call this one capital A, call this one capital B, just so you don't have to keep writing double bar V, double bar U.
Yay.
So, same thing applies. This is a static system. He's hanging onto the rope, and let's assume he's resting at this time. So he's, not trying to move anywhere. And the crocodiles down below are trying to scare him.
Yep.
So we're going to take all of these, add them all together, and it should add up to the zero vector,
Which is 0, 0, right?
which is 0, 0. So the first component is going to be the sum of all the first components. You might want to find out what cosine of 171.5 is and the cosine of 3.7.
Cosine of 171.5 is negative 0.99.
0.99. And the cosine of 0.37?
I don't know, I'm still writing this down.
Oh.
It is 0.99.
Cosine of 0.37?
Yeah,
Really?
9.
yeah. So
That's
one's negative,
strange.
one's positive.
That's really strange. Do I trust you?
Okay, you said cosine, right? Cosine of 171.5. Got negative 0.99. Cosine of 3.7. 0.99.
Well, that's strange. It's actually, if you're rounding to the nearest hundredth, it's 1.
But then you just round it to the nearest one.
Bird.
Well, I'd rather have them be different, trust me, than exactly the same. That would just be weird.
Bird.
Technically, you should go 4 decimal places, but we'll stick with these 2. All right, so the first component of the first one is 0. The next one is magnitude of U times negative 0.99,
So it's negative 0.99a.
0.99a. And the third one is going to be 1 times the magnitude of V, so that'll be plus
B.
B, comma. That's the first component of all the vectors, I position. J position, first one is negative 200 plus, well actually, erase that.
You find the sine of 171.5 is right.
Yep, sine of 171.5, and it's going to be plus
0.15.
0.15. So it'll be plus 0.15 times
A.
Plus the last one was sine of 3.7, Should be really
0.06.
0.06. So it would be plus 0.06 times b. First component, second component, and this is equal to the 0 vector.
So you set the first one equal to 0, the second one equal to 0?
Mm-hmm. Now, here's the fun part. Like the sine one of the equations only had an a or a b in it, and you could solve for it and then plug it into the other one. This one's going to have an a and b in both of them, so it becomes known as a system of equations. So I'm going to give you a technique to solve it. You should have been taught it someplace in your past, but you might not have.
Probably not.
All right, so if I set them both equal to 0, I get negative 0.99a plus b is equal to 0, the first component of the 0 vector. The other one I'm going to get fancy with. If it's going to be equal to 0, I'm going to move the 200 to the other side. So it becomes 0.15a plus 0.06b is equal to 200. Actually, we don't need to do a system of equations. We can do a simple setup. What do you think we should do to get a equal to something and b equal to something? What looks nice and easy? Left-hand side or right-hand side?
You take out a plus b.
Can't factor it out. Oh, would be nice,
That would be.
but it doesn't work that way. They have to have something in common. So what can I do to the left-hand one to help me out?
Set it equal to b.
Get it solved for b. So if we solve this for b, we're going to get b is equal to 0.99 of a. That's
So you
legal.
plug in b to the other side.
Right, so take this little piece and shove it in the other side. So I'm going to replace all the b's with 0.99a. So this becomes 0.15a plus 0.06 times 0.99a is equal to 200. So far this thing is behaving. Alright. What the heck is 0.06 times 0.99?
0.0594.
0.0594a plus that 0.15a up front for a grand total of 0.2094a is equal to 200. So far so good. Alright, just simple algebra. And then divide both sides by that ugly decimal, and you get a is equal to
955.1.
955.1. Now, what was a to begin with?
A was a magnitude of u.
So this is the magnitude of u, and this is pounds. Even though Indiana only weighs 200 pounds, Illinois, Jones, only weighs 200 pounds, the rope on the u side has to be able to withstand 955 pounds of force. It's a pretty thick rope. All right, how do I find b?
So he's pretty safe.
Ooh, I don't know about that. He better go
Well,
across the cable.
Unless he falls off.
Unless he falls off. How do I find b?
You plug in what a is to the other side, so good.
And come over here and actually just put it right back into this box.
Yeah.
So it's 0.99 of this, 99% of it if you want to think of it. So b is going to equal
945.5.
945.5 pounds, and this was the magnitude of 8. So the rope on the longer trip has to hold a little bit less weight than the rope on the shorter trip. So if he runs into trouble, you better go backwards.
So,
And that's just holding them
I
still.
was about to say the rope would have to hold.
A total of,
I mean, if you get closer towards that side, the angle
It's gonna hold
increases.
more.
They have to hold more.
yeah. So as you get closer to the edge, the rope has to be stronger.
Yep.
Strangely enough. And the other side doesn't even hold that much weight. Oh, same thing for gondolas. You know, those things that take you up hills and whatnot. Gondolas. Yep. Alright, so that pretty much ends up all the vector stuff.
Yeah.
Well, all the vector stuff up into plane. You think I'm done?
Yeah.
No.
There's no time.
There's time.
There's no time.
There's time.
No, there's not.
There's always time.
There's always time.
There's always time. So let me get you ready for the next section. Simple